can be reduced from one problem to another problem. In the sense, given say an arbitrary graph with no edge weights, I want to determine whether there exists a 2, which is called a Hamiltonian circuit, in the graph or not. So I want really a solution for a Hamiltonian circuit problem, but I don't have an algorithm for solving the Hamiltonian circuit problem. On the other hand, let's say I have an algorithm to solve the traveling salesman problem. So what we are going to see is, can we make use of the algorithm for the traveling salesman problem and use the solution of what we get from the traveling salesman problem to infer the solution of Hamiltonian circuit problem. So this is like a transform and conquer technique. We don't have an algorithm to solve a problem right away, but we are going to transform that problem to some other problem for which there is an algorithm to solve that problem. And we are going to solve the problem as the the new version, the transform problem, and use that solution to infer the solution of the original problem. Okay. Alright, so let us see an example to understand this. So we have a graph, right? So A, B, D, C, D. Now we want to decide whether this graph has a Hamiltonian circuit or not. Of course, when you should look at it, it's a 2. We can say yes, it has Hamiltonian circuit, but how do we do it algorithmically? So let us say there's no algorithm for this problem that can give you a solution in polynomial time, a decision solution in polynomial time. On the other hand, let us say there is some hypothetical algorithm for the traveling salesman problem that can give you the optimal solution in polynomial time, because it's an optimization problem, a traveling salesman problem. Alright, so what I'm going to do is, I'm going to first transform the Hamiltonian circuit problem to a traveling salesman problem. So remember, the input for a Hamiltonian circuit problem is some arbitrary graph with no edge weights. Whereas for the traveling salesman problem, you need to have a complete graph with some edge weights. So I need to build a complete graph based on the given graph. So the way we build this complete graph is, again, we have the same set of vertices A, B, C, D. Now we have to have complete graph, means an edge between any two vertices and some edge weight for those weights, so for those edges. So if there is an edge already in the given graph between two vertices, we retain that edge in the complete graph also, and the weight of such edges is 1. So AD, the weight is 1, BD, the weight is 1, BC, the weight is 1, AC, the weight is 1. Now for any two vertices that don't have an edge between them in the given graph or the original graph, we have an edge between them in the complete graph such that the weight of such edges is greater than 1. So let us say the weight of such edges is 2 in this case. So between A and B, there's no edge in the original graph. So we have an edge between A and B here now, and the weight of such edge is 2. Similarly, C and D did not have an edge originally, so now they have an edge of weight 2. So now we have a complete graph of some edge weights for every edge. So let's run that algorithm, which I said will give you the optimal solution. Optimum means the minimum weight 2 on this complete graph. So let us say we come up with ACBDA as the optimal 2. Now what we have to check is, there is the sum of the edge weights, so which we can also call as the weight of the tour, is, and in this case we are minimizing, trying to find the minimum weight 2. So is the minimum weight of a tour that we came up with same as the number of vertices in the graph? So if all these edge weights are 1, which is indeed in this case A, C, C, B, B, D, D, A, so all edge weights are 1. So if you add up all the edge weights, it is 4. That's also same as the number of vertices. So if the weight of the optimal tour is same as the number of vertices in the graph, what it implies, all the edges that are part of the tour are of weight 1. Okay, because in a tour you have to have all the vertices and the starting vertex is kind of repeating. So the number of edges is going to be the same as the number of vertices. So if the weight of the tour is same as the number of vertices, then all the edges in that tour have a weight of 1. And if all the edges in the tour have a weight of 1, it also means those edges were there in the original graph. Because the way we built this G star, which is the graph for the traveling salesman problem, is there's an edge, if the edge weight is 1, if that edge is there in the original graph also. If the edge weight is other than 1, greater than 1, say in this case 2, then that edge is not there in the original graph. Now, if all the edge weights add up to the number of vertices, that means every edge is of weight 1, then that means all the edges that are part of the tour are also part of the original graph. That means we can say the original graph has a tour because all those edges are part of the original graph, and we have come up with the tour for the original graph. So we have an yes or no answer. In this case, yes answer if all the edge weights added to the number of vertices. What if all the edge weight, if the sum of the edge weights does not add up to the number of vertices? It will be more than the number of vertices. Like in this case, if you start up with a graph that does not have a tour and to build a complete graph out of it, and so whatever you try for this complete graph and run the algorithm, you will not be able to find a tour such that the sum of the edge weights will add up to the number of vertices. Means you will not be able to find a tour where all edge weights are 1. Okay, so the tours that you could come up with will have at least one edge of weight 2. There cannot be a tour such that all edge weights in the second G star are all 1. Why? Because the original graph that we used to build this complete graph does not have a tour. If it had a tour, we'll be able to come up with a tour such that all edge weights are 1, okay, in the complete graph. So that's the idea. So you build the complete graph out of the original graph with edge weights distributed like this. And if you're not able to find a minimum weight tool for the traveling salesman problem on this complete graph such that the sum of the edge weights is the same as the number of vertices, it means there is at least one edge that is part of the minimum weight tour that is of weight other than 1. That means it is not part of the original graph. That means the original graph does not have a tour, because if for the original graph to have a tour, we should be able to find a tour of all the edge weights of 1. So in this case, that means the original graph does not have a tour. Okay. So what we have seen now is this is called polynomial time reduction, because this the time it takes to build this complete graph out of this given graph is polynomial time, because you have, say, v vertices, and all you are doing here is considering all pairs of vertices. So that is v times v minus 1 over 2, which is v squared. So you spend v squared time to consider all pairs of vertices and then decide if there is an edge between them in the original graph or not, and accordingly assign the edge weights. So the time complexity of this, what is called polynomial time reduction, is v squared in this case, which is a polynomial. So so we call it as a reduction because we are able, it's basically transformation. To solve the Hamiltonian circuit problem, we transform that to a traveling salesman problem in polynomial time, that is v squared time. And by applying a polynomial time algorithm for the traveling salesman problem, that is also, it's again a polynomial time, so it's like you spend polynomial time to transform to a traveling salesman problem, solve the traveling salesman problem in polynomial time. So that means overall you can obtain the solution for the Hamiltonian circuit problem also in polynomial time. So that means if you have polynomial time algorithm for the other problem you are transforming to, you can say we are able to find the solution for the original problem also in polynomial time. So that is the benefit that you come up with what is called polynomial time reduction. So as long as this transformation, in this case the transformation is building the complete graph out of the given graph, can be done in polynomial time, then the original problem can also be, and the second problem also has a polynomial time algorithm, then the original problem can also be solved in polynomial time. So that is kind of how we look at polynomial time reduction. Okay, and let us now look at some application of polynomial time reductions, and then we'll move on from there. So let me quickly save this video.